Если ответила, скинь, пожалуйста. Мне очень сильно интересно, я переживаю за свою ляльку.
I'm surprised no one's here. I'm late. Thought I was walking in on the lecture.
Салют, приятно.
Oh, really? Okay, that's good.
Very. Кешетті ғой бәке жүріп келдің ба не?
Жоқ.
Жақын. Сен кеше бізге келген соң келдің ба?
Иә.
Прямо, да?
Иә. Сен үйің басында тұрған, үйің басында келіп қалғанда соқтың ғой. Сосын мен қанша уақыт сен неше?
7 минут жүріп, 10 минут.
Сен 9-да соқтың, 20 минут келдің.
Ой? Дочын суға қалай ма? Үйреніп жатыр ма? Мінекей алтыншы жаста қалай?
2-3 күн сағат. Finish.
Пакет зарядка армасында?
Иә.
Шнур, иә. 5 шнур зарядка ғой.
Оңдан жүрсін.
А?
Оңдан жүрсін бе?
Неге апарып едің ғой? Какие? Samsung центрге. Олар айтады, iMain тексерді, артындағы iMain. Айтады, сен Европаның Union'да алған жоқсың ғой, пошел отсюда говорит. Типа такого отшили же есть. Үшінші елден келдің ғой, үшінші елде алдың ғой, зарядка бар елінде деп. Сондайға келтірдік да, sorry, мынау. Типа, у тебя телефон не для Европы, не для... Мен боқтап білдім. Үшінші елді сынайды бізді. Саған айттым ба лекарство туралы? Өткен жібек айттым ба?
Мен айттым өзім.
Жоқ, лекарство туралы.
Когда тестируете.
Жоқ, тестируете емес. Бір, местный неге кірген, онлайн чат обсуждать етеді ғой, местный англичанкілер, витамин туралы.
Оған дейін білесің бе?
Что, доктордың өзі жазған үшінші елдерге кететін?
Ибуфен білесің бе?
Ибуфен? Иә.
Сол бізге тестируете ғой.
Қой?
Қазақстан, Россия тестируете.
Балдарға ма?
Я сейчас по Франции, Англии захотели.
Ибуфенді? Қа тұрғын мой көрдің облыста?
Запрещен во Франции на 4. Типа тест не прошел в 3 момент.
Жестко, да? Хотя біз учили Англияда алғанда бізде дочкада аллергия бар ғой. Врачқа барған кезде айтты ғой, біз қазір одно лекарство разрабатываем. Хотите туда? Ну, будем делать тест на вашего ребенка. Слушай, айтты, ақша төлейміз дейді. 10 фунт на это. Короче, оны айтты, порошок, соны бір жыл сол порошокты бересің дейді. Сосын аллергия либо кетеді, либо кетпейді. Бірақ ол жақта жазылып тұр, кәдімгі қағаз, бәрі брошюр, бәрі түсіндіріп тұр, жазылды. Оно точно тестируется, бірақ мы не можем сказать, что конкретно уйдет или не уйдет, это уже будет видно через год. Каждый, допустим, месяц будете приходить. По-моему, как другой играл целый. Слишком много знаешь, слишком много говоришь.
Енді шамадан көрген нәрсе болашақта оңды нәрсе
СК формация дейді. 1,3 миллиард теңге штраф салды ғой формация. 1,3 миллиарда оштрафовали на 1,3 миллиарда тенге за нарушение антимонопольного законодательства. Ашық жоқ қой дальше закон кезеді. Жұмыс еткізді ғой өзі. Өзі жұмыс еткізіп алады да, ұрлатып да, бәрі.
Сен айттың
Отырғызады шешесіне.
айттың ғой сен айтып неге етті беріп алып содан кейін сүт беріп отыр. Болмайды көріп отыр. Итке басында ет бересің ғой, ет жегісі аты қауыл атты. Бағана Австралияда досыммен сөйлестім.
Дос бар ма не?
Аха, бүйтесіз ғой, бүйтесіз.
Чего?
Күш кетті ғой.
А неге ма? Навсегда, что ли? Қой?
Елсіз оққан бағам.
Сіз оққан ба еще?
Елсіз оққан жақта Австралияда магистратура.
Австралияда ма?
Тройка біздің
Лучше тройку да. Нифига себе. Қатты оққан болып тұр ғой. Заң болып тұр ғой. Кәдімгі семьясымен бе жаңа сөз?
гражданский бәріп тұр ғой. Оққан не болғаннан сұраған кетеді ғой. Австралияға 3 жыл сол.
Ну, походу, өзі родители қалып қойды, да? Өзі өшті.
Мақан бәйт сол ғой.
Мақан?
Мақан не бұрат болып кетті. Папасы екі жейін болды.
Өзі ғой. Разработчик знания.
Morning.
Что?
Oh, right. It must be too dangerous. Yeah. Yeah, this is just horrible smell. It's like rainy smell.
То олар бәрі переселенецтер ғой.
Oh, and Newcastle, it's like.
То переселенецтер өзі.
We're not miles on it's new place. I came down and tried
Жоқ, қошып кетті, енді қашан алады? Әлі қарады ма не?
So we like that,
That was yesterday. I just decided not to come Yeah. Yeah, no, I agree.
Ақша қашасы бар, қанды қадашын бе?
I'm very scared. And different groups are helping me a bit with.
Короче, аптасына дейді. Мен уже айына 4 мыңнан көк аламын.
Oh, what are you doing for your?
Enerjisi. So when you do gas loss, but as soon as yield when you hide test, you can ignore a bit of that. But eventually, products and then really it is quite a bit less than yields. They want to know why. For all the standards, so you've got to see
Новый пособник обязан
or you
оставить.
can resupply one needs to resupply concrete. But then it's less than that. You still want to know why. You can easily assume that it's less than that. And then tell customers that they're not doing a repair and say, no.
That's a bit true.
You must assume it's you.
Ah, yeah.
You must assume it's you.
Everyone got their
No, the main one should be released system. But I went in a couple of weeks ago and asked about did they select it because it's back by mistake.
Really?
I know what I got. So I've got the physical copy, it's not released on that yet.
Yeah, mine hadn't been released, but I got an email yesterday.
Сейчас ваши газеты работают.
But I'm just surprised it took so long. But maybe they were holding on to it. Because they normally email you as soon as it comes in. Well, that's what they're supposed to do. So it's weird.
Алан видео, 3 месяца я штрафовал всех, я устроил. Короче, полная блокировка живота, да?
Well, when I was in the office, I read like another course that I was almost to get and they were saying that I was raising it to be like 20
The materials.
or just any but then a lot of stuff was always delayed. Like I remember with Kevin actually did it in March.
That's
So,
good. They've selected that.
yeah, so it could be that we don't get it back to the beginning.
Ощущение будет иметь какую-то республику. Нигде.
These are got
Просто там довольно много, плотно, но слоя массы развит очень количество. Обещанным буду говорить.
You never know what if they give you like really
Да?
Дайын алуларды айтылған.
Come back right now. It's quite
Oh yeah. I got long bin town.
Alright.
He doesn't do any of
So,
that.
yeah,
He's
that
good
colour is
for I think he used to do it.
So you're doing a dynamic space?
Yeah, it's kind of it's but it's
Ну да, хотя я чувствую, что это даром
yeah, that's the heat one.
Оппозиционный мирный içinde
Good project, I think you have to work really hard for this.
Крысоват?
Utkler bu.
Не утку.
Kulübün karşılıklı klimat projesinin adamı. Мысалы, сен оппозиция барсың, мен сен оппозицияны салып қоямын, мен бір кітап проектісін адамын. Сен оппозицияда жүріп түк боласың да маған.
Специально, да?
Сондай деген ауызбіршілік оппозиция.
Part of my pipes are doing
А, оппозиция где-то
fire around columns.
Это не было мастеров.
I know, I such but I did I miss out much yesterday? Well, I never pay attention anyway, so I was just let me go, so I'm not sure what I have to do this time.
Короче, я түсіндім, олар көрдім. Ана кімдер ма? Кім олар? Фейсбукте жазады ғой постоянно. Видеоға түсіріп. Президентский не деп. Президентский наследомайство, не исполняйте деп.
Ол емес, оның бәрі цифровой клевый.
Да?
Оны байқамайсың, ойлайсың да
Just that you I'll be used for it. I'll be working on the yards. Probably My computer.
Your mind feels weird. Like a race.
So that's induction, that's what we get there. Screen so you put them on, it's just a right action.
Ne oldu senin de?
I would
Aklına duruyorsun.
It is because when you're doing it in decommission, so most people have to be considered something like fast switch.
I don't even mean that, for the outline. The outline is the the carbon sensor pipes are very stiff compared to some of the GE pipes where like that carbon
Well, what's strange is that in GE they actually just use one value for the different they don't even split the layers.
yeah, that's what I mean, but the different constructions will have different values
Yeah.
for different types of construction. Even though you use one value for a composite pipe, for a composite of different lengths, it's going to be different values. I'd email them back now. Just ask them for information from you, something this way. We're asking if there was any difference for composites and stuff to different construction types.
Чемпионский тур албанийский движение вообще. Еще максимум я не прикол.
Carbon composite houses? Because with some kind of what should be bought then? Sort of thought as it last before the steel pipe of them. Semi-submersible as well.
Well,
So the fact that
some
people
of
use
the
it.
they haven't actually started using field jets.
So they got points of control. They've got points of control.
Okay, good morning. So yesterday we looked at the engineering properties of soils and rocks. And then we looked at seepage permeability. And just to introduce you to engineering properties like permeability, hydration. So today I'm going to talk about a different aspect here, which is the shear strength of soils, okay? Which is very important when you design your structure, pipeline structures and so on. So, do you know what is shear strength? Shear strength? We come across this word, shear strength? Yeah? It's the ability of material to resist shear forces, yes? Okay, so talk to you about shear strength of soil. So when you bury a pipeline or a footing or a pile in the ground, it has to resist these shear stresses and shear strains. So before I do that, I would like to introduce one of the most important concepts I was talking about yesterday, this one of effective stress. If you want to learn something from this lecture, that would be this principle, okay? And I'll introduce it in a very simple way. So if you consider that a soil layer, and then you have your water table at the top, so it coincides with the ground surface, and you look at the soil element here, let's say pipeline buried at this depth, or a soil that will be taken out to be tested in the laboratory. So we know that we are going to look at the stresses acting on this soil element or soil sample. First of all, we know that this soil is saturated because the water table is at the top. So it has gamma sat, and I showed you yesterday what we mean by gamma sat. That's the saturated unit weight. So how do you calculate the stress? Let's say the vertical stress acting on this sample. Sigma V equals unit weight, saturated unit weights times Z. That would be the vertical stress. At the same time, we have also a forward pressure that is acting on the soil sample, which is equal to the depth times the unit weight of water. Instead of soil, we get water. Now, if you take this forward pressure from the total stress, this is total stress. This is forward pressure. So sigma V minus forward pressure gives you the effective stress in the vertical direction, okay? Later on we talk about what's happening in the horizontal direction. So that's basically the principle of effective stress, is effective stress equals total stress minus forward pressure. It's very simple, very powerful. It's very powerful principle in soil mechanics, because the deformation and shear stress and everything is controlled by the effective stress, not total stress. Okay? So you have to always calculate the pore pressure, take it from the total stress in order to get the effective stress. So that's the what I just showed you. So the total stress, gamma sat times Z, forward pressure, that's unit weight of water times Z. Effective stress is sigma minus U equals gamma sat minus gamma, the unit weight of water. So this is called the principle of effective stress, and it was recognized or developed by Terzaghi in 1925. Okay, before that, all the design was done based on total stress. And the principle of effective stress is an important principle in soil mechanics. This is what we teach our students in geotechnical engineering, second year, third year, fourth year, which is there about the importance of this principle, because then we know that the deformations of soils are function of effective stress and not total stress. And the principle applies only to normal stresses, not to shear stresses. Can you tell me why it applies only to normal stresses and not shear stresses? Why this principle applies to... Can you write something like tau effective equals tau total minus forward pressure? This is the shear part. Let's say this is normal stress. Can you write it in this form? Why it applies only to normal stresses and not shear stresses?
So shear stress not going to depend on grain angle and all the rest of that?
For the simple reason is that this part here, forward pressure, you cannot shear forward pressure. There is no shear stress for forward pressure. Forward pressure is hydrostatic. Okay? Can you shear water? So the shear stress of water is zero. You can compress water, but you cannot shear water. So that's the shear part of pore pressure is zero, basically, because it doesn't have any shear stress that water can sustain. You can compress water, apply hydrostatic pressure, but you cannot do that. So in general, what you write is total stress, total shear stress equal to effective stress. Okay, so you end up with this principle applied only to normal stresses. Okay. There's an example that we need to revisit in a few minutes before we move on, or maybe just finish the lecture and then we can come back to this example. Now, if we look at the same sample here, we just calculated the vertical effective stress, the forward pressure, and the effective vertical stress. Is there any other stresses that are acting on the soil sample? So So to be in equilibrium, so it's subject to vertical stresses. Is there any other stresses acting on the soil sample? If you have only vertical stresses, then it will not be in equilibrium. It must have, or it must be subjected to also horizontal stresses in that direction. Yeah? So the key is how you calculate those horizontal stresses. So sigma dashed h, it's a big problem. We don't know how you calculate those horizontal stresses. There is one way to do that, is to relate them to the vertical stresses via a coefficient called K0, which is the coefficient of earth pressure at rest. This is another material property that I'm introducing. So K0 is equal, basically, effective horizontal stress divided by effective vertical stress. Okay? So if we know the vertical effective stress and we know K0, we can indirectly or rearrange that equation to calculate the horizontal stresses. So K0 is called the coefficient of earth pressure at rest. So when there is nothing, so you have the horizontal stresses in equilibrium with the vertical stress, you can calculate K0, and that is called the coefficient of earth pressure at rest. Sometimes we relate that K0 equals 1 minus the friction angle. So the friction is another material properties that I will introduce later on when we look at shear strength. So it can be related. So if you know the friction part of the material or the friction angle, then you can calculate K0, and from K0 you can calculate horizontal stresses. It's very important, these horizontal stresses. So if in the case of K0 less than 1, it means that the horizontal stresses are smaller than the vertical. So the position of your ground would have been like in a vertical, so you have sedimentation. Now imagine K0 greater than 1. What does it mean, K0 greater than 1? It means the horizontal stresses are greater than the vertical. And this happens only if we have like tectonic stresses happen in the past. So let's compress the ground in the horizontal direction. So you end up with horizontal stresses greater than the vertical one. So this is just an indirect way to measure horizontal stresses. So if you know sigma v and K0, you can access or you can estimate the horizontal stresses. And again, please observe that this K0 is given in terms of effective properties. When I put dash here, it means that the equation is relates to the effective part of the stresses. I'm not writing it as K0 equals sigma h divided by sigma v. It doesn't work. It has to be written in terms of effective stress. So when you see dashed, this symbol here, it means that the quantity is effective. You have to take out the pore pressure from the total stress. So there is an example that we can also revisit later on when we finish the lecture. So this is very simple, as you can see. It's just a very simple equation. Total stress minus pore watts pressure equals effective stress. But it's very powerful concept to be applied in soil mechanics. And this I'll show you why. Because this is like a brief introduction to shear strength. Why do you need shear strength? Shear strength is very important when we design against failure. Okay, if you have like slope stability problem or footing or a pile or pipeline and you're trying to look or quantify stability failure, then that would be controlled by the shear strength. Okay, I said yesterday deformation is controlled by stiffness and failure is controlled by strength. So knowledge of shear strength is required in the solution of problem concerning stability failure. So if you want to assess your structure against failure, you have to know about the shear strength. For example, stability of slopes. If you want to estimate the ultimate bearing capacity of a foundation, a pile or footing problem, offshore foundation. If you have a retaining wall excavation and you want to look at the failure of this excavation wall, then you need to know about shear strength. and piles. If you design piles, you need to know about shear strength. However, in 1776, I showed you yesterday the most important people who contributed in this field. MAR Coulomb. Coulomb is one of the engineers who contributed in this field. He postulated that the maximum resistance to shear, that's the maximum resistance to shear, is on failure is equal to C plus sigma tangent phi. So that's the equation. This is the maximum shear that a soil can sustain, and it is done in terms of two parts. The first one is like a cohesion, the cohesive part, that C is the cohesion of the material. The second part is the friction. So you have two material properties here, which are C and phi. This is called cohesion, and this is called friction. So you have two parameters, or two contributing terms, that work together to resist shear. Okay? So the shear, the maximum shear stress that a soil can sustain is equal to C plus the normal stress, let's say the depth times the unit weight, times the tangent of the friction angle. So those are two terms, or two material properties that control the maximum resistance to shear. So we are introducing those two material properties. Later on, I'll tell you how we obtain them from laboratory experiments. Okay, they can also be estimated from lab tests. But what can you say about this equation if you look at it? MAR Coulomb. The Coulomb failure criteria. What have you heard about Coulomb failure criteria, by the way? No? So what if you look at it, how is it expressed? It is expressed in terms, can you see dashed here? No. So it's expressed in terms of total stress, and that's what has been used or was used from 1776 until 1925, when Terzaghi came up with his effective stress principle. So sigma is the total, is the normal stress, that's the stress in the field, and C is the cohesion, phi is the friction angle, and so on. But Coulomb's equation did not always result in a successful design of soil structure, because it was always used in terms of total stress. And I said to you earlier on that deformation and soil behavior is controlled by effective stress. So if you use this equation in terms of total stress, as you can see here, sigma and C and phi, they are expressed in total as total quantity. The design is not successful. So the reason for this did not become apparent until, as I said, 1925, when Terzaghi introduced this principle of effective stress. And then now, if you rewrite this MAR Coulomb failure criteria in terms of effective properties, so you write it in tau. There is no tau dashed because I said water doesn't have any shear resistance, so just tau equals tau dashed equals C dashed plus sigma dashed tangent phi dashed. So all these properties are given in terms of effective properties. So in which phi and C dashed are properties of the soil skeleton, effective properties, effective angle of friction and effective cohesion. If you design your structure, slope or pile or foundation in terms of those effective properties, you get successful design. Okay. So next question: how are we going to estimate these values? Determination of shear strength of soils. Yesterday I introduced to you the permeability, and I showed you two tests which can be used to calculate permeability: constant head test and falling head test. You can also do it in the field. Carry out what we call pumping out test to estimate the permeability. Yeah. Today I'm showing you two tests which are used to estimate those two properties: the friction and the cohesion of a soil material. So the first one is called direct shear test. Okay, so what does it mean, direct shear test? So you take your sample and you put it in a box. That's the box there. That is your sample. Okay, that's the soil sample. You put it in a box. So this pink the box is divided into two parts. So the pink part is fixed, and the top part can move with respect to this fixed bottom half part. Okay. So what we are trying to do here is we are trying to shear the sample along this line. So if you push the top, if the bottom half is fixed and we push the top half, then we can shear the sample along this line. So this is like a predetermined failure plane. So if you push the sample along that line, we can quantify or measure its resistance to shear. Okay, we can see or measure how the soil resists the shear stress as we push the top half. So, but before you do the test, you take your sample, put it in the shear box test, and apply a normal load here. That is, we said tau equals C plus sigma tangent phi dashed dashed dashed. So that load is basically sigma dash. That's the normal stress that you see in the field. Imagine you have a soil here, and your pipe is going to be installed here. So that stress sigma equals gamma sat minus unit weight of water times Z. That's what you need to apply on the sample when you take it to the ground, from the ground to the lab. Okay, that's sigma, and you push your soil along this predetermined plane by using this shear stress here, or shear force. So it's a force, you push the half bottom. So T, if you divide T by the cross-sectional area of the sample, don't forget it's a box. Okay, so it's a box like that. So half of it is fixed, half of it can move in a horizontal direction. So now if you divide this force T by the area, okay, the area that you are trying to shear the sample on. So T divided by A gives the shear stress. Okay, so you can measure the shear stress along this plane as you push the top half during the test. Okay, and the normal stress sigma equals N divided by the cross-sectional area or the area of the sample. So the sigma will be N, that's force here, divided by the area, and the shear stress will be the force, this force divided by the area. Okay, so what we do with that, once we have carried out the test, okay, so we start with N1, force N1, let's say, or shear stress N1, sorry, normal stress. So that's N1 divided by A, that gives sigma normal 1, and you shear the sample. So you push the sample into failure under a constant normal stress, and you get an idea about the shear stress that causes failure in the sample. That will be T divided by A, and that will be 1. That's the shear stress under which the soil failed under this normal stress. Then you change your normal stress, N2 divided by A gives a second normal stress, and the soil will fail under a different shear stress, let's say call it tau 2, and you repeat the test 3 times, equals sigma dash 3, and you get a third shear stress failure. Then you can plot your data in terms of failure, shear stress versus normal stress. So you have 3 stresses, sigma 1 corresponds to failure tau 1. You have sigma 2 correspond to a different shear stress at failure, and then you have another test carried out at sigma 3, which causes failure at tau 3. So you have 3 points. So if you plot the gradient or the line that joins those points, okay, let's say it's a line that joins those 3 points. That would be your failure criterion that proposed by MAR Coulomb, which is tau equals c dashed plus sigma n tangent of phi dashed. So that line basically defines that line here. That is the failure criteria tau equals c dashed plus sigma n tangent phi dashed. So the gradient, you can measure the gradient of this line, and that gives you phi dashed. And the intercept of the blue line, which is the MAR Coulomb failure criterion with y-axis, gives you c, or c dashed. That's that value there, c dashed. Okay, and the gradient of this line is phi dashed. So you get the two properties from this simple test, direct shear test. So you have to carry out 3 tests. You fail your sample at 3 different normal stresses. Then you plot your data, okay? And the gradient of this line would be the friction angle, and the intercept with the vertical axis gives you the cohesion. So now, just from this test, doing the test 3 times, we can estimate c dashed and phi dashed, and those are the strength material properties. Okay, so those are those 2 material properties. Okay, so now if I ask you a question about what is happening below this line and what is happening above, now what can happen below this line and what can happen above that line. So imagine you have a soil that is subject to this stress state. So sigma n, I don't know what, and then tau would be that. So it's that point there. Is that point going to cause failure or not? No, because it's below. So if you assess the stability of your structure, knowing c dashed and phi dashed, if you know this line, okay, and then you know your stress point, you just look if it is below that line, it means that failure will not happen in the structure. Now, if your stress point is going to take your sample to meet with this line, then that means that your soil has already, as soon as it touches that line, it means it failed. Okay, this is what we call this stress space here. Is called possible stress space. Anything above this line here, you can never reach this space because the soil would have failed before even you reach that line. So this is called impossible stress space. Okay, so that line separates. That's the failure criteria. Separates possible stress conditions from impossible stress conditions. And this line is basically defined in terms of c dashed and phi dashed, those 2 strength material properties. So if you look at this test now, can you tell me what are the problems? What would be the problem?
You have to measure pore pressure, convert from stress to...
That's correct. So in this case, it's very difficult to measure pore pressure in this test. That's the difficulty of this direct shear test or the shear box test. Pore pressure is difficult to measure, so usually it's done in terms of total properties. And this also restricted to coarse grained soils like sand. It's difficult to put clays in this box. So is there any other problem you can see on this happening on this or that can develop in this test? Think about the way you push the sample.
You're going to get a different area as soon as it starts moving.
Yes, as soon as you start from this area, which is this one. Now imagine you push that top half until this point. So the area now is just this one. Okay. So first of all, you start losing samples, particles, because as you push this top half, soil particles start to come out of the box, and the area also reduces during the test. So the area is not constant. And the main problem, basically, we are forcing the sample to fail along this line, which is not always happening in the field. Failure can happen at any given plane. Okay, it's not forced along this predetermined failure plane. So there are a few problems with this direct shear apparatus. But it's good to get to use it to, especially for coarse-grained soil, to obtain C dashed and phi dashed. That's fine. However, we can improve on that. But first of all, let's see how the soil will behave in this shear box before I move to another test. So if we consider those two configurations, okay, this is the first configuration here. Okay, can you see what's happening? The difference between the two? Sorry? Particles. So think about voids. Voids. You see the voids here? Okay. So the void spaces are what? Maximum, yeah? This is like a very loose soil because you have a lot of voids here. This is a very compacted soil because the voids are very small because the particles are compacted with each other. So the blue configuration is basically called the dense soil. It's very dense, it's very compact. You have less voids between the particles. This one is a loose soil. So when you shear them in the shear box test, they show different behavior. Okay? So when you shear them in that box and you plot your data in terms of stress versus strain, axial stress, axial strain, or in terms of volume change, there is N missing there. So you see the dense soil shows a very high peak. So it has a very high shear resistance. And then followed by softening. And it converges to this value, which is critical shear stress. However, the loose sand or the loose soil is continuously hardening, doesn't show any peak, but ultimately it converges to the same critical value as a dense. If you keep shearing the sample and you apply a lot of deformation, both of them converge to the same residual value, which is this one. Okay, and it's usually taken to design your structure, these residual values. But a dense soil shows a very high peak, which is not observed for loose sand. In terms of volume change, you see that if you have a soil that has a lot of void spaces, like this one, if you shear the soil, what you get is just a continuous contractancy, what we call just a reduction in volume. So the volume always reduces in this case, because if you shear this configuration, the samples will drop in this space, so you get a reduction in volume, a reduction in space. Yeah. This one, this configuration, this dense, if you try to shear it, so the particles at the top don't have enough space to move. So the first thing they do, they try to create space around them. So first they have to go up from that space. They go up before you can shear them. That's what we observe. You get some kind of dilation. All the time they try to increase in volume. And this is the difference in behavior between these two samples. One being very compact and one being very loose. And you can see this observation in just a simple shear box test. So sample with a higher density, compacted soils, shows a peak load. That's a peak load there. The specimen first contract and then dilate. So first it contract and then dilate to make space between particles, so they can move and they can be sheared and resist shear stress. However, a sample with low density, that is not compacted, shows no peak load, and the specimen exhibits contraction always reduction in volume. Okay, those are the two different behavior we see in typical soils. These are values for friction angles given by Terzaghi. So you see, if the soil is loose, the friction angle tends to be lower than if when the soil is dense. So for a loose uniform sand has 28 degrees of friction. However, in a dense state, it has 34. So dense soil resists better shear stresses. Okay. So what are the limitations of the test? We went through them very quickly. So the sample is constrained to fail along a predetermined plane. Okay, you are forcing the soil to fail along that line. And due to end and side effects in the rigid box, the stresses distribution on the failure plane is not uniform because the area is changing constantly as you push the top half box. Pore pressure cannot be measured during the test. It can be measured, but you have to design like a very sophisticated shear box test. This is like the research level. I'm sure there exists shear box test equipment to measure pore pressure, but we are talking about the usual experimental work that we do day to day to carry out site investigation and lab investigation. So it will be difficult to measure pore pressure, and to improve on that, there is a very famous experimental equipment called triaxial. Have you heard about triaxial? Have you heard about this equipment? No? This is extensively used in geotechnical engineering. It's again to measure the shear strength of the material, C dashed and phi dashed. We can use a triaxial test. How does it work? You see here, that's the shear. That's the triaxial. So it's a cylinder filled with water. Okay. So this is a cylinder. Okay. It's a chamber. Plexiglass. Here you can see the sample. Inside the sample is there, installed inside the triaxial cell. And then first, what you do, the cell is filled with water. So first you increase the pressure in water. And this is to apply on the sample the normal stress, as we did in the shear box. We apply the normal stress. So in the first stage is to ramp up the pressure in water, so it can apply like hydrostatic pressure on the sample. And then you can shear the sample by applying a vertical stress using this plunger. So once you reach that normal stress using the water pressure, you apply a vertical stress to squeeze the sample, crush the sample, fail the sample in the triaxial. So here, as you can see, the soil can fail on a different plane. It's not predetermined. It can fail at 45 degrees. It can fail like a barrel. I'll show you the failure mode later on. You see the sample is placed between two porous discs. You see those two porous discs here? This is when you squeeze the sample, water can escape from the sample. So if you want to measure pore pressure inside the sample, then all you need to do is to close the valves. You see the valves here? The valves. So you close the valves, and then you squeeze the sample, and then water can escape from the sample. And because we are closing the valves here, we can measure how pore pressure develops in the sample, how excess pore pressure increases. Now, if you open the valves here, and then we apply our stress to crush the sample, then water can escape, and then that would be a completely drained condition, so pore pressure does not play any role. In this case, you are not interested to know what is the pore pressure in the sample. And this is very important because measuring pore pressure or not is not it is done for a purpose. You want to know the stability in a long term. Stability in a long term means after 5 years, 10 years, you would expect pore pressure to dissipate during that time. Yes? So pore pressure doesn't play any role in a long term. However, stability in the short term, after 2 weeks or 1 month, you still have excess pore water pressure in the sample, or in the road, or in your pipelines around. Pore pressure is still there, so you have to know how much excess pore pressure in the sample. So those are the two different scenarios. When you check for your stability, you have to look at stability in a long term, where pore pressure is not involved, and stability in a short term, after a few weeks, 2 weeks, 1 month, when pore pressure is still exists in the system. And the stability is completely different, especially if you look at slope stability problems. Pore pressure has a huge and significant effect on stability. In a long term, pore pressure can dissipate and your effective stress can increase. So if you have effective stress equals total stress minus pore water pressure, in the short term, this is very high. So your effective stress is low, so you have less stability. In a long term, this goes to 0. And as this goes to 0, this increases, your effective stress increases. Basically, the contact between the particles and the stresses that hold the structure increases the effective stress, and that would improve the stability of your structure. So we can do those two scenarios in the triaxial. First, we close the valves and measure pore pressure inside, or we can open the valves and let the water escape, and then we'll be measuring the properties in terms of long term, in terms of total. Okay, so very quickly I'll go through what we can do in this test, in this apparatus. First, we can do consolidated drain, as I explained. So you consolidate your sample to the in situ stress, and then you shear it. This is called consolidated drained. This is consolidated and drained. So you close the valves and you make your sample end drained. It cannot, water cannot escape from the sample. And by doing so, you measure pore water pressure. And those two tests help us to estimate the friction as well as the cohesion. How does it work? It works exactly in the same way as I'll go through it very quickly. So, have you heard about MAR circle of stress, representation of stress?
Yes.
Yes? You can do the same thing for strain, but here, what we are going to use it is to plot the same failure criterion, which is tau equals C dashed plus sigma n tangent phi dashed. Okay, so we are trying to use the triaxial test to obtain this and this. Okay, so how are we going to do? So first we have our triaxial test sample. We apply what we call sigma 3. That's the radial stress applied through water. And then we apply sigma 1, which is the vertical stress to fail the sample. We could do the same thing as before. We can plot sigma 1 and sigma 3. So we start with a stress, a radial stress or horizontal stress that is used through this by increasing pore pressure in the water system. So let's say we start from 100 kilopascal, all right, sigma 3. That would be the stress, the confining stress around the sample applied by the water system. And then once we reach 100, we start from 0, we increase it to 100. Then once we reach this value, we start increasing sigma 1, and sigma 1 start to increase, okay, until we reach failure. Okay, so we record this value here, sigma 1, which caused failure in the sample. Okay, forget about this test now. That's our first test. Now we start from a different confining stress, let's say now 150, and we start ramping sigma 1. And sigma 1, we record sigma 1 that causes failure in the sample. That's sigma 1. So now we have two circles corresponding to failure starting from a different confining stress. If we imagine now we start from a lowest confining stress 50, for example, and we increase sigma 1 which will cause failure in the sample, and we just record the last point, which is this one. Now we have 3 circles, 1, 2, and 3, in which we recorded failure of the sample. What we do is we plot the best tangent to these 3 circles, okay? And the gradient of this line is basically the friction angle, and the intercept here with the vertical axis is C dashed. Okay? So you get C dashed and phi dashed from the same from the structure by conducting and taking 3 tests. And recording sigma 1, sigma. Each time you have to record sigma 1 and sigma 3, the confining stress, and sigma 1, which causes failure. Sigma 3 and sigma 1, which causes failure. You start the third test, sigma 1 and sigma 3, which causes failure. And the best tangent to those 3 lines, 3 circles, is this line, from which you can calculate the friction angle. What happens if the line intercept the y-axis at 0, like this one, like here? What does it mean? C equals 0. Huh? Yes, so cohesion. This is called frictional material. You have only friction, you don't have cohesion. Okay, this is usually for sand. For sand, usually C dashed equals 0. And for clays, C dashed is different than 0, is greater than 0, okay? So that's what happens if your line, if you test a sandy soil, always intersect the vertical line at the origin. So there is no cohesion in sand. As you can see, you go to the beach, you don't have particles sticking together, okay? So you don't have. All right, example. I'll give you a couple of examples which you can do at home. Again, consolidated and drained. Here we just measure pore pressure. We do again the same thing. We measure pore pressure, so you can plot your 3 circles in terms of total stress. Okay, that's the continuous lines, the blue, the red, and the green. Those are more circles of failure in the sample under 3 different stresses, confining stresses. But because we are measuring also pore pressure at the same time, okay, so if you take your circles, okay, oh sorry, the dotted lines are the total stresses, sorry, the dotted lines are the total stresses, so are the more circle in terms of total quantities. Now if you subtract from those the pore pressure which we measured during the test, we get those continuous lines, which are the circle or failure stresses in terms of effective. Okay, what can you observe here? The effective properties, like friction here, is higher than the total one. Why?
Water pore pressure.
Yes, exactly. Because if you take into account pore pressure, you would expect your strength to reduce and the stability to reduce. Now, if you let your pore pressure dissipate, okay, then that would cause your effective stress to increase, and you get higher friction angle and higher cohesion. Okay, so this test is good because you can get at the same time the total effective, the total strength and the effective strength properties at the same time during the same test. Okay, I'll give you an example here, so you can do this. But we still have like half an hour. I would like to go back to this example on effective stress. Maybe you can have a break, 5 minutes break, and then we come back to this, because I think it's very important to know how you use this effective stress in a practical situation. So if you have 5 minutes break, and then we come back and we do this test, and then. First of all, do you have any questions about this shear strength properties, C dash, phi dash, and how you get them from? They control stability and failure. I showed you 2 tests from which you access those properties or estimate. Do you have any questions about this topic? Okay. If not, so we can have 5 minutes. break, and then when we come back, we do this test, this example.
Blackboard about what?
Sorry?
No, I'm asking him.
I can't understand what you're asking here.
No. You said we have 5 minutes break.
Yes.
Yeah.
Okay.
I'm just asking the question from him.
I said if you have any question, and you said something I don't understand.
I'm asking from my friend.
Okay.
Var mı idi?
Excuse me.
Yes.
Can you visually see that a soil sample has failed? Like,
Of course, yes.
what
I'll show you. Sorry?
Okay.
They usually do that.
He was awake around 3.
You have failure?
Yeah.
He told me I'm afraid of
So you have something like that? They slip?
landing to
Okay.
You can slip. Sorry, visually, yes, of course, you see it.
You see.
Some they don't fail, they just do that.
Just maybe.
Bar. This is like failure. This never fails because
Meeting out tomorrow.
you get something like that. This one, if you have clear failure, they just do that.
Wasn't that exam due?
So shall we be able to see that in the lab today?
Oh yes, we can show you example of failure, yeah, and sample, yes. Yeah. I'll show you some
Then
in the lab.
the shear stress test, the one of separating the 2 boxes.
Yes.
Can we do that in the field, or is it only done in the lab?
How do you do that in the field?
It's not possible.
No, it's just simple box. Yes, you can do it in the. There are other tests you can do in the field.
No.
You have something like that.
Test.
Yeah, permeability test can be done.
It's very expensive.
It's very expensive. No.
Yeah, you said very expensive. Yeah, on the field test.
So you
Permeability.
have something like that, which you insert in the soil, and then you apply torque.
You keep
Yeah.
rotating this.
Yeah.
These are like
You can blades. Yeah, you can do that in the sample in the field. That also get like.
So you keep turning
Yeah.
until
Yeah, this is what we do. Yeah, something like that. Yeah, you keep pushing here, you keep turning, and you measure the resistance. You get the force you apply here, or the torque,
yeah.
versus how the displacement, how it turns. So initially it does this, and then that gives you more or less the same what happened here in terms of tau versus displacement. Sorry. So there are different techniques to do in the field, in the labs. I'm just presenting stuff very simple in the labs. Yeah. Because they are small.
General.
It depends on the project. If the project is very expensive, like offshore structures,
Yeah.
you have a lot of money to invest. You can do site investigation. If it's just a house or a building, you don't have enough money to do this. Just do laboratory tests. So it depends on the nature of the project.
Just to see
It's
the
like-
strength of the soil.
Yes, if it's like £1 million more, then you can have a look at use more advanced techniques in the field to measure these properties. Yeah, it's like a long pipeline. You can do this site investigation. Usually it's called CPT tests.
CPT.
Yeah, con. Sorry.
I haven't seen you guys in ages.
Penetration.
Test. So it's something like that.
Probably Monday was when the last came in.
Okay, that you push in the ground, and as it's pushed in the ground, it measures. It can measure pore pressure. It can measure the friction here.
It's an equipment.
Sorry.
It's an equipment. You just put it in the soil.
Yeah, but
and
it's very, very expensive.
it does the measurement.
Yes, and then you can record the measurements and use that to get the strength of the soil.
Okay.
But those are expensive tests.
Thank you.
All right. Yeah.
I've only been to the library and got uploads of books and that's it. And it just like shows up in my I need, well, I've got some papers to read through on my computer. And I've asked for send me some standards, for some standards I need to read library research, which is unusual.
was referring to this that it still wants to prevent all the leaches to
Yeah.
And then what you do is
Oh, Microsoft.
and by final production,
Like it's a smart home, isn't it?
Yes, we were the we see each other and that's like always definitely like that. Make like acrobatic
Is Daddy really like?
even the very few times it failed.
She looked a
Feels
little.
okay. For sex. Strong found, but
he doesn't really use like fried physics because when he like impressive, he doesn't
So
know
about doing experiments on seawater, especially
he's
seawater.
pretty much freedom, but he doesn't like go all the way
In the
down.
library.
I can only do 10
Like the
grams.
homepage.
yeah.
But on my legs, 17.
Just
But I've got really weak legs.
I know, but where, in Google or in library?
No, you are really in the general arm, like,
Just feel like knock out the first person that gives me
actually I found one for
Very, very useful for you.
Oh yeah, it's great.
Do you have it?
when
Really? I couldn't find any.
He gets tired easily, very, very easily. Like he can barely run 1 kilometer.
I need to get back into the gym. Just going for Christmas is making me really unfit. So I'm trying to go back. Because I can't run for as long as I used to.
I use the reduction but the fatigue is
Oh yeah, but it's and I've got a membership to be on.
I was walking to the gym today. It was like kind of snowing.
I explained the proposal here.
Yeah, well also, you're running around like GMT. So I
If we apply much there,
But it's really sticky.
already itchy.
Ian.
so this is we need to talk about
The only thing I like about what you do is that now
No,
I can
he didn't say it. So I asked him, "Would you try what
see
we
for a year.
And at the end of one sentence, I will do that.
this one.
This one did this one did this one like this, this one like this.
Like it felt so tricky. It was around 12:30. So I felt behind.
Okay, so can you make start please on this one? 6 and then we can move to the go to the lab in 15-20 minutes from now. Okay, so the first step to calculate the effective stress, you need to calculate total stress, pore water pressure, then you subtract the two and you get effective stress, okay? But to calculate total stress, you need something. Unit weights. Yes. So let's calculate the unit weights. Okay, so here we have the ground surface. The water table is located 2 meters below. That's the ground surface. This is like 10 meters. This is 2 meters. And we're looking at a point or soil sample that is situated at 5 meters. Okay? So, first of all, we have a layer here that is above the water table that's going to be dry. And this is below the water table that's going to be saturated. So we need to calculate the dry unit weight, gamma dry, equals GS divided by 1 plus E times unit weight of water. So that's equal 2.6. Yes, 2.6. Is it 2.6? 2.7. 2.7 divided by 1 plus 0.7 times unit weight of water 10. That gives you gamma dry of 27 divided by 1.7 equals 15.88 kilonewton per meter cubed. We need to calculate the saturated unit weight. So gamma sat equals GS plus E divided 1 plus E times unit weight of water equals 2.7 plus 0.7 divided 1 plus 0.7 times 10. Okay, and you get gamma sat equals 2.7 plus 0.7 divided by 1.7 equals 20, yeah? Kilonewton per meter cubed. Okay. Then we have to calculate at that point total stress. So total stress that is equal to 2 meters of dry soil plus 3 meters of saturated soil. So gamma sigma V equals 2 meters times gamma dry plus 3 meters of soil times gamma sat. That equals 2 times 15.88 plus 3 times 20, that's 60, plus 30, 90, 91.6. That is kilonewton per meter squared because it's stress, okay? Then we have to calculate pore water pressure. Pore water pressure at that depth at 5 meters. 5 meters. This is total stress at 5 meters.
The first case in the dry unit weight, you have it multiplied with 10.
It's multiplied by 10.
Yeah, you just write 227 by 120.
2.7 times 10 is 27. Yeah?
The point was not clear.
Which point?
2.7.
That point.
Yeah, when we calculated, in our calculation, when we did,
Oh yes,
we missed up, sorry.
that's fine. So the pore water pressure equals, because here from the saturated, from the water table to the point is only 3 meters. So it's 3 meters times unit weight of water. 3 times, can you see what I'm writing here? Yeah? It's 3 times unit weight of water. That's 3 times 10 equals 30 kilonewtons per meter squared. Okay, and finally the effective stress at 5 meters. Okay, effective stress at 5 meters. So sigma dashed equals total stress minus pore water pressure. 91.6 minus 30 equals 61.6 kilonewton per meter squared. Okay, that's the effective stress. So if you want to plot the distribution of these things, we can. This is how you should do it. So you have the groundwater, the ground surface, the water table here, and our point is situated at 5 meters. Let's say 0 to 5 meters. Okay, and then we can plot it in terms of total stress, pore water pressure, and effective stress. Okay, so the total stress starts from 0 and increases with depth. So the first 2 meters is 2 meters times gamma dry, that is 31.6. So this value is 31.6, and then plus 3 meters times 20, that gives you 91.6. So this is given in kilonewtons per meter squared. Pore water pressure given in kilonewtons per meter squared, and effective stress kilonewtons per meter squared. Okay, that is our distribution of total stress. The effective stress, the pore water pressure would be 0 here because it's dry, and then start to increase linearly from 2 meters. So it's 3 meters times 10, that's 30. Okay, that is our pore pressure distribution with depth. This is effective total stress distribution with depth. Now if you subtract the two, you have effective stress equals total stress minus pore water pressure. You get 0 minus 0 is 0. 31.6 minus 0, it goes to 31.6. And then at 5 meters, you get 91.6 minus 30, that is 61.6. And that is the effective stress distribution with depth, okay? It's only calculated at 5 meters depth. It can change at 5 meters, 6 meters, 7 meters, and so on. It's just to show you how the distribution of these three things, pore pressure, total stress, and effective stress. Okay, so I think I have covered my part, but soil characteristics, engineering properties, shear strength, permeability, and so on. So if you go to the lab now, and I have my PhD students waiting for you to show you a few experiments, how you, hopefully you relate what I have been talking about to this small experiments. So do you know where the labs I explained to you yesterday? Yeah, it's in the Drummond building. Yes.
So we have maybe later you can send us answers to some of the other questions.
It's easy, I mean, the other one. I mean, it's easy. If you show me, don't you, I can.
Yeah. So I think you solved them already.
Sorry, it's very, very simple. I mean, they're not very difficult to really right type them. If you do them, you come and see me. I'll go through them with you. Yeah.
Thank you so much.
Yeah. Okay, any questions? No? Okay, I'll see you in the German. I have to go and print out the notes for you. But I'll see you in the German in 2 minutes. In the ground floor. So, do you know where the place? The number is just ground floor, okay? So take me to
What time do you
I just thought you had it.
That's the left. So, alright, so give us
And you will happy to meet you. Yeah,
I also maybe